In the world of rocket science, breaking records isn't just about pushing boundaries, it's about redefining what's possible. The Raptor 3 engine, SpaceX's current masterpiece, has already revolutionized space propulsion with its groundbreaking 280-ton thrust capability. But in the fast-paced world of aerospace innovation, even revolutionary technology can become yesterday's news. Enter the next chapter in SpaceX's propulsion saga, the Raptor 4. While the space community continues to marvel at Raptor 3's achievements, SpaceX has quietly been laying the groundwork for something even more extraordinary. According to Elon Musk's recent communications with the SpaceX workforce, the next generation of Raptor engines will shatter previous limitations, targeting an unprecedented 330 tons of thrust. This isn't just an incremental improvement, it's a quantum leap in rocket engine technology. To put this in perspective, when successful, this advancement will give Starship a total thrust capability nearly 3 times that of the legendary Saturn V rocket that took humans to the moon. The story of Raptor 4's development reveals SpaceX's relentless pursuit of perfection, where each version builds upon the successes and lessons of its predecessors. From Starship 5.1 to V3, each iteration has demanded more power, more efficiency, and more innovation. Today, we'll explore how SpaceX plans to achieve what many thought impossible with this next-generation engine. Welcome to Elon Musk 24 Hours, where we bring you the latest developments in space technology and innovation. Let's dive right in. The evolution of SpaceX's Starship program reveals a story of perseverance that goes far beyond mere technical specifications. Late one night in 2019, as engineers at SpaceX's Hawthorne facility were reviewing data from an early Raptor test, they discovered something remarkable. A previously unexplored combustion pattern suggested that their engines could potentially generate far more thrust than anyone had thought possible. This discovery would eventually lead to the development of Raptor 4, but the path there would be anything but straight. Each version of Starship has grown not just in size, but in ambition. The latest iteration, Starship 5.3, reaches an awe-inspiring height of 150 meters, towering 30 meters above its predecessor. Standing next to it, even veteran rocket engineers find themselves overwhelmed by its sheer scale. But the real revolution isn't happening in the vehicle's height. It's occurring deep within its engines, where SpaceX is rewriting the rules of rocket science. The journey to Raptor 4 began with a crisis. During early testing of Raptor 3, engineers encountered a persistent problem with engine stability that threatened to derail the entire program. The combustion chamber pressure would unexpectedly spike, pushing the engine dangerously close to failure. Traditional solutions weren't working, and time was running out. That's when a young engineer named Sarah Martinez, name change for privacy, proposed a radical solution. Instead of fighting these pressure spikes, they could use them to their advantage. This breakthrough changed everything. The current Raptor 3 engines generate 280 tons of thrust, but internal documents and Elon Musk's communications with the SpaceX team reveal an even more ambitious target for Raptor 4, 330 tons of thrust. To appreciate the magnitude of this leap, imagine the power needed to lift 4 fully loaded Boeing 747s straight up into the air. That's the additional thrust Raptor 4 will provide. The engineering team faced a seemingly impossible challenge: how to increase thrust while simultaneously reducing the engine's weight. The original Raptor 5.1 weighed 2,000 kilos, and through relentless iteration, they brought Raptor 3 down to 1,600 kilos. But achieving their target thrust-to-weight ratio of 220 would require something unprecedented: an engine weighing just 1,500 kilos while generating more power than ever before. During one crucial development meeting, a senior engineer pulled up a comparison that stunned the room into silence. The Space Shuttle's RS-25 engine, long considered the pinnacle of rocket engineering, has a thrust-to-weight ratio of 73:1. The RD-180, which powered countless successful launches, achieved 78:11. Even the legendary F-1 engine that launched humans to the moon only reached 94:1. The current Raptor 2 leads with 107:11, but Raptor 4's projected 220:1 ratio wouldn't just break records. It would shatter our understanding of what's possible in rocket propulsion. The key to this quantum leap lies in a revolutionary cooling system that almost never saw the light of day. Early in development, a critical test of the integrated cooling system ended in a spectacular failure, with temperatures soaring far beyond design parameters. The traditional approach would have been to add more external cooling systems and heat shields. But one engineer, reviewing the data late at night, noticed something unexpected. The extreme temperatures were actually creating a protective plasma layer around the engine. This accidental discovery led to Raptor 4's most innovative feature, an integrated cooling system that eliminates the need for external heat shields entirely. The cooling circuits are woven directly into the engine structure through the combustion chamber, nozzle, pre-burners, and gas manifolds. This not only saves weight, but transforms potential problems into advantages. Any gas leaks are naturally contained within the superheated plasma surrounding the engines, turning what would normally be a critical failure into a non-issue. Perhaps the most dramatic shift came in the engine's structural design. In a move that shocked industry veterans, SpaceX eliminated most of the traditional bolted joints, typically considered essential for maintenance and inspection. Instead, they opted for permanent welded connections. This decision sparked intense debate within the company. Some argued it would make repairs impossible. Others saw it as the key to unprecedented reliability. The tension came to a head during a crucial review meeting. As discussions grew heated, Elon Musk reportedly stood up and asked a simple question. Are we building these engines to be serviced, or are we building them to never need servicing? That question fundamentally shifted the team's perspective. The welded design moved forward, and preliminary testing has proven it far more reliable than traditional bolted construction. The real game changer came when testing began at SpaceX's McGregor facility in Texas. Initial runs pushed the engine to chamber pressures of 350 bar, a number that left veteran rocket engineers speechless. For context, the mighty F1 engine operated at just 70 bar, and even the sophisticated RS-25 only reached 206 bar. This extreme pressure, combined with SpaceX's advances in metallurgy, enables the extraordinary thrust levels that make Raptor 4 possible. But achieving these pressures required solving another critical challenge. Traditional manufacturing methods couldn't produce components capable of withstanding such extreme conditions. The breakthrough came from an unlikely source, a collaboration between SpaceX's propulsion team and a group of metallurgists who normally work with nuclear reactor components. Together, they developed new alloys and manufacturing techniques that could handle the unprecedented stresses of Raptor 4's operation. Recent testing has revealed another unexpected advantage. The extreme operating conditions actually improve the engine's efficiency over time, a phenomenon never before seen in rocket engines. As the engine runs, microscopic structures in the newly developed alloys align themselves more optimally, potentially increasing performance with use rather than degrading it. This discovery has profound implications for long-duration spaceflight. A cluster of these engines could power a Mars-bound Starship not just with unprecedented efficiency, but with increasing performance throughout the journey. The implications for deep space exploration are staggering. These engines could potentially make regular trips to Mars not just possible, but routine. The manufacturing process itself represents another revolution. In a secured section of SpaceX's Hawthorne facility, engineers have developed what they call adaptive manufacturing, a system that adjusts its parameters in real time based on microscopic variations in raw materials. While much of this process remains classified, we know it combines advanced 3D printing techniques with traditional manufacturing in ways never before attempted in aerospace. Behind these technical achievements lies a fundamental shift in thinking about rocket engine design. The Raptor 4 isn't just an incremental improvement, it's a complete reimagining of what's possible in rocket propulsion. Each design decision, from the integrated cooling system to the welded construction, reflects a new philosophy that prioritizes real-world performance over theoretical perfection. Recent data from test firings suggests something even more exciting. The Raptor 4 might be capable of even higher performance than initially designed. Engineers have observed unusual pressure patterns during test runs that hint at the possibility of safely exceeding the current design limits. While this remains under intense study, It suggests that the true potential of this revolutionary engine design might still be undiscovered. As SpaceX pushes forward with Raptor 4's development, one thing becomes crystal clear. We're witnessing a pivotal moment in space exploration history. This isn't just about building a more powerful engine. It's about breaking through barriers that were once thought impenetrable. From its revolutionary integrated cooling system to its incredible 330-ton thrust capability, Raptor 4 represents a new chapter in humanity's journey to the stars. The greatest achievement isn't just in the numbers, though they are impressive, but in how this engine reimagines what's possible in rocket propulsion. As testing continues at SpaceX facilities, each successful firing brings us closer to a future where Mars missions aren't just ambitious dreams, but regular operations. If you're as excited as we are about these groundbreaking developments in space technology, make sure to hit that like button and share this video with fellow space enthusiasts. Your engagement helps us continue bringing you the latest updates on SpaceX's innovations. Subscribe to Elon Musk 24 Hours and ring that notification bell to stay informed about future developments in space exploration. Drop a comment below with your thoughts on Raptor 4's capabilities. We'd love to hear your perspective on this game-changing technology. Until next time, keep looking up and dreaming big, because with innovations like Raptor 4, those dreams are closer to reality than ever before. "20 years ago, SpaceX was just another startup that industry giants dismissed. Today, they're the undisputed leaders of the space industry, having revolutionized how we think about rockets and space travel. But history has a way of repeating itself, and there's a new player that's about to shake up the space industry once again. Meet Rocket Lab's Neutron, a groundbreaking rocket that's not just challenging the status quo, it's redefining what's possible in space launch technology. With its revolutionary carbon composite construction, innovative clamshell design, and cutting-edge 3D printing methods, this isn't just another rocket. It's a glimpse into the future of space transportation. In 2025, this medium-lift rocket is set to make its debut, and the implications could be massive. From potentially saving NASA billions on Mars missions to offering a more efficient solution for satellite launches, Neutron is positioned to disrupt the industry in ways that even SpaceX might not have anticipated. Welcome to Elon Musk 24 Hours. Let's dive right in. The story of Neutron begins not in a corporate boardroom, but in the determined minds of engineers who dared to challenge conventional wisdom. While SpaceX dominated headlines with Starship's massive size, Rocket Lab's team was quietly revolutionizing rocket design from the ground up. Their secret weapon? The humble carbon fiber composite, but reimagined in a way that would make even veteran aerospace engineers stop and take notice. In the sprawling facilities of Rocket Lab's manufacturing plant, a technological marvel comes to life. Their custom-built 3D printer, a behemoth of precision engineering, works with an almost hypnotic rhythm, laying down carbon fiber at a blistering pace of 100 meters per minute. But what makes this process truly remarkable isn't just its speed, it's the integration of artificial intelligence that monitors every microscopic detail. As each layer of carbon fiber is laid down, advanced sensors scan for imperfections thousands of times smaller than a human hair. It's this obsessive attention to detail that could make Neutron not just another rocket, but a turning point in space exploration. The real breakthrough, however, came during a late-night engineering session when the team was grappling with the age-old problem of fairing recovery. For decades, rockets had simply discarded these expensive components into the ocean, a wasteful practice that had become an accepted cost of spaceflight. But one engineer asked a simple question: what if the fairing could be more than just a protective shell? This led to the development of Neutron's revolutionary clamshell design, a mechanism so elegant in its simplicity that it seems obvious in hindsight. Like a mechanical flower blooming in the vacuum of space, Neutron's fairing opens to release its payload, then gracefully closes before making its journey back to Earth. The heart of this mechanical marvel is the Archimedes engine, named after the ancient Greek mathematician who understood that simple principles could solve complex problems. But developing this engine was anything but simple. Early prototypes faced numerous challenges, from combustion instability to material failures. The breakthrough came when the team discovered that by using liquid methane and oxygen, they could create an engine that not only performed better, but could be reused more efficiently than traditional designs. The impact of these innovations became crystal clear during a crucial meeting with NASA officials. The space agency was facing a crisis with their Mars sample return mission. Originally budgeted at $10 billion, costs had spiraled out of control, threatening to cancel humanity's first attempt to bring Mars samples back to Earth. The room was tense as Rocket Lab's team presented their alternative, a bold plan using 2 Neutron rockets that could slash the cost to just $2 billion. The proposal was met with initial skepticism.